but I had a few questions at the beginning of the lecture regarding what was actually to do today. What you did last week, you're going to have the opportunity to do again today. So a lot of you collected good data last week, and you were able to analyze it and get an empty coefficient out of it. The spring rate, I think everybody was able to get fairly easily, but a lot of you tried to process this stuff over the weekend or last week, and you noticed that you didn't really have high enough break rate to do anything useful. Okay, so you'll have the opportunity to do that again today. Now, hopefully, because it's your second time around, it'll be faster in terms of collecting the data. With regards to what's due, there is some deliverables next week. I'll talk about those at the end of the lecture, but it's going to incorporate your K and C that you've got from the experiment last week, which you had the opportunity to repeat this week, as well as some experimental data that we're going to collect from that RC car there. Okay, so I'll talk about that in a little bit. But there's a lab demonstration today, just for sake of the agenda. There's two things mainly that we're going to be doing. The first thing is vehicle system dynamics related, obviously. So we're going to be doing an active suspension lab that incorporates this device right here. So I'll talk about that in more detail in a little bit. The second thing is the RC car experiments, which are on that table over there. So the room configuration kind of changed to facilitate these two things. The second thing, is design activity 3 discussion. So what are you actually responsible for next week? And then how is this incorporated into the response paper? Okay, so I'll go over some MATLAB corner car models because I haven't really talked about what you need to do for that yet. So I've posted a lot of literature on Learn with some good MATLAB models that you can use as a reference to create your own. Okay, and then I'll talk about the actual hard deliverables for next week. So the first thing that I'm going to do is demonstrate an active suspension system. So I guess as an intro, we talked about suspension quite a lot in terms of how it incorporates into a vehicle and why it's important to minimize the sprung mass acceleration for ride comfort, handling, and road holding. So all those things. So on a typical vehicle, you have cheap suspension, for lack of a better term. The stiffness and the damping are pretty much constant, and it's a compromise of a wide range of properties so that you can get good performance, or let's say reasonable performance, on a wide range of scenarios. Okay, so a passive system just has fixed values when you operate it. So there's no active feedback loop in the system to optimize either the stiffness, the damping coefficient for purposes of ride comfort, or minimizing or body roll, or optimizing ride quality, those things. So on the left we have a traditional passive system that has adjustable damping. So the device here that I'm holding is what the picture is on the left. It's from a typical sportier car. There's a spring like we all see. At the top there's a damping adjustment for the rebound damping here. Sorry, this is the compression damping, and the rebound at the bottom. And then you can adjust how this mounts so that you can change the extended length of this. Okay, and then you can adjust this collar to change the amount of load that's on the spring. And that will effectively change the activation force of when the spring is becoming used. Okay, so all that stuff is kind of inside, but feel free when we're doing the lab part over here to come take a look at this. But the important thing here to notice is that there's a dial at the top that you can turn. And this is changing the orifices inside the bypass system in the body of the handle. Okay, so these orifices allow fluid to travel between them, and that's what's damping the system. Okay, so if you manipulate the orifice the way the fluid travels through it, you can change the amount of damping. However, it's pretty inconvenient to go wherever this is located in the car. You might see a bumpy road and you say, hey, I want to adjust this. So you got to get out of the car, you have to open the hood, or you have to go into the trunk, or it might not even be easily accessible, and you have to go to all 4 corners and manually adjust this. It seems fairly impractical. So more than likely, it's acting as a passive system. You set the dampening for your desired application, and then you leave it. If you change the application dramatically, you might readjust the damping. If you add a lot of sprung mass to the vehicle, or you change the unsprung mass, you might change the damping, and that's easily done. You can also exchange the springs if you want. Everything's removable so that you can exchange the spring here to change the spring force, just like these that you saw in the previous lecture that everyone worked with. Okay, this one's damaged, but you remember what they look like. So that's what a passive system is. They've been around for decades, and it's a pretty simple system. Adding the adjustability to top is a minor incremental improvement. What I'm showing now on the right is an active system, and this is obviously not something you would put into a vehicle. It's a lab demonstration to illustrate the idea of active suspension. But what it effectively has is underneath there's a DC motor with a belt that turns this actuator rod, or it turns so that the actuator rod can reciprocate up and down, and it effectively applies motion into this lower plate like this, okay? And then above this lower plate are springs, and all of these two plates are supported by springs here, okay? So there's a spring here holding up the unsprung mass. That's what this device is here. There's not any meaningful damping between the road actuation plate and the unsprung mass because there's only springs. Once again, there's similar springs between the unsprung mass and the sprung mass. So you can see two plates of weight over here. That's representing kind of the user or the person operating the vehicle, okay? So this is the sprung mass here, and this is the sprung plate, so to speak. So this is the seat of the car, so to speak, okay? That's what the user's riding on. So minimizing the acceleration on this is kind of equivalent to improving the ride quality. You can imagine if I had a small cup of water here, and I'll use this analogy a few times because we're going to get this thing to shake around a lot. If I had a small cup of water sitting here, sorry, my water bottle doesn't fit. If this plate has too much transmitted acceleration, you're not going to be able to drive with your coffee in your hand or in the cup holder. It's going to spill over. Okay, that's the crude analogy, but we saw those ride quality criteria, those ISO standards in the last lecture for the duration, the frequency, and the amplitude. So what the criteria is to meet the ride comfort for a rider in a passenger vehicle, okay? The neat thing about this is that there is a whole bunch of sensors and instrumentation on it, and there's this servo motor that you can use to apply forces between these two plates. Okay, so this servo motor is attached to, there's a pulley with two ropes or cables on it, and it's attached to both of these plates. Okay, so I can control the servo motor via this USB cable to the computer here, and I'll show you in a little bit what that means. But that's the cool part of this. I can change the characteristics of the servo motor to change the dampening characteristics of the system. Okay, and I'll show you exactly how that works in a little bit. So there's a few accelerometers on here. We'll be looking at that data as well. There's an amplifier that takes all the signals here from the device, and it goes into this data acquisition box here, and that data acquisition box is communicating with MATLAB on my computer that we'll be able to see on the screen in a little bit. Okay? Before we get started, I'm gonna, in the process of not making this a passive, no pun intended, lecture, I'm gonna step through a quiz with everyone that will be for marks, but everyone will be able to get 100%, hopefully, if you're listening. It's on Learn, and we're going to go through all these steps of how this works, just so that people can follow along, because not everyone can actually sit close to this and see it. You will see it moving from the entire classroom, but the quiz is going to be step by step. I'll ask a question, you'll have some time to think about it, and we'll discuss it a little bit. Everyone will answer, and then I'm going to show you exactly what it does on the machine. So I'll ask you, like, how does the unsprung mass affect the response of the sprung mass? What would happen if you changed the stiffness of the spring? What would happen if you increase the amplitude of the bump? That type of thing, okay? So, skip here to the next slide. If everyone wants to bring up quiz, it's on Learn, it's called Active Suspension Lab Quiz. This is mainly just for you, and we're going to take up the responses right away. This is mainly just for you to be a little more active in this lecture, so hopefully you're going to retain this stuff for a while, okay? If you have any questions, the quiz is somewhat open book in the sense that you can ask me something. I'm not going to tell you directly the answer, but if you ask me a good question, I'll give you a hint. Okay? There's a password to the quiz. It's called suspension. Everyone should be able to log on to it now. Not able to log on to it, raise your hand. When you get into the quiz, this should be the first question. If you don't see this, let me know. It says, from a fundamental point of view, how many degrees of freedom does this active suspension device have? Okay, so please don't skip ahead. The purpose of this is to do it question by question, and then as we take up the question, I'm going to give everyone the opportunity to move to the next question. So don't move ahead, because I can see the timestamp when you move to the next question. Once we move ahead. It needs to be done in sequence. Like I said, everyone's going to get the answer by the end of it. I'm just forcing you to put it in so that it goes from your mind to your hands, and that connection is made. Okay? So from a fundamental point of view, how many degrees of freedom does this have? Who remembers what the difference between the single degree of freedom quarter car model was and the 2 degree of freedom? What was it? I hear sprung mass or unsprung mass. Which one is it? So this device has a sprung mass. Okay? That's this here. It also has an unsprung mass, which is this. So I think it's pretty self-evident. This question is pretty much a gimme here. And I'm going to prevent kind of and this isn't a trick here because a few of you are probably considering the option 3 because there's 2 spatial degrees of freedom and then there's 1 dampening degree of freedom. Okay, I'm going to encourage you to think back to the time response plot or the transmissibility plot or the frequency response plot for a 2 degree of freedom system from the previous lectures. Okay. You saw all of those different curves. I'm gonna move to this diagram here. You saw all these different curves here, and the different curves represent different damping characteristics. Okay, so you're representing on a 2 degree of freedom system here a whole bunch of damping characteristics or zeta terms via all these responses. Okay, so it's still a 2 degree of freedom system. So when I go back to the question here, everyone should see that the answer is, who wants to raise their hand and answer now? Shouldn't be 0 because the system isn't statically determined. There's more than 1 degree of freedom. Okay, so that answer is off the board right away. We talked about how a single degree of freedom system doesn't have an unsprung mass. This one does have an unsprung mass, so it's not a single degree of freedom system. And I just kind of alluded to you that the dampening can be represented on the same plot for a 2 degree of freedom system. It just changes the response. It doesn't change how many nodes are in the response. The node identification is how you can say how many degrees of freedom there are. So by method of deduction there, it's 2. Okay, so hopefully everyone can get to 2. We're going to move to the next question. Sorry for patronizing everybody with going through this first question very slow, but this is the process how it's going to happen. Okay, so the next question is basically asking you to identify all of the different components of this system. Okay, it's a match question. You have to match the word to the number. If you're confused about where the arrows are pointing, raise your hand and I'll come clarify it. What you're seeing on the screen is exactly what you're seeing in front of you here. Give you guys about a minute or two to complete this one. By question 3, it gets a lot more interesting. The first few are just to make sure that you know what I'm talking about when I move to the next questions. It's just terminology. Most of them populated by now, but I'll show what the answers are now. As I mentioned previously, there's a sprung mass here, sprung mass plate, which is effectively showing the displacement of the sprung mass. So measuring the location of this plate is the displacement of the sprung mass, because everything that's mounted to that plate is rigid in between. There's an unsprung mass plate, which is this red plate here. The DC motor is pretty obvious. That's what's actuating the whole system and exciting it from the bottom. The road actuation plate is this bottom plate here, the silver plate. The unsprung spring is between the road. This is effectively modeling the tire. It's between the road and the unsprung mass. Okay, so this is the tire stiffness here, which is not in this analogy here, because this is only a 1 degree of freedom model. Then there's the sprung mass spring, and that's between the unsprung mass and the sprung mass, so that's directly modeling this spring here. Okay? And then there's a closed loop adaptive damper with position sensing. So I didn't talk about that in much detail yet because we haven't discussed how it works exactly, but that's the device here that I was pointing to. Okay, that's applying the damping force between the unsprung mass and the sprung mass. So that's pointing to this servo motor here. Okay? So hopefully everybody can input those answers. I'll give you another 30 seconds or so to move to the next question. If you have any questions, or you disagree with anything, or you just want to clarify, like I said, this is a pretty much open book quiz, so just raise your hand and we'll talk about it. All right, next question. Sure.
So, like the unsprung spring, what exactly, like, defines the unsprung?
So, it's not supported by the real spring of the car. It's just the inverted stiffness between the roll and suspension of the car. So, if you think about, imagine doing concrete tires on the car. Okay? Whatever the roll would do is what your suspension would do. However, we have nice pushy rubber tires, which means that there's some stiffness that's not infinite between the roll and your suspension. So that's all that this is modeling, and you'll see how it varies how the distance between these two plates will vary. If this was effectively super rigid, and the distance between those plates will remain very close together, or sorry, it would remain almost constant. It's almost like driving on concrete tires. Okay, so good question, but the unsprung spring, which are these two orange springs here, that's representing tire stiffness. Any other questions? Anything else I can clarify? So that, like I said already, is not being shown here. We're excluding the tire from this. This is just the top part, from the red to the blue. Okay. Next question is, based on the frequency response of a typical 2 degree of freedom system or core model, will the sprung and unsprung masses follow the road profile identically? So this is kind of what I just talked about. So I'll give you about 20 seconds to think about it a little bit, then I'll talk. All right, so there's a few key words in the question that will allow you to deduce the answer. I think by sheer common sense, if you read the part, will the sprung and unsprung masses follow the road profile identically? What that actually means is that if you drive over a bump, whatever the bump profile is what the unsprung mass is going to do, and it's exactly what the sprung mass is going to do. So what does that mean about the stiffness between the road and the mass? The sprung mass. It's approximately infinite. Okay, it means that it's rigid between here and here. Whatever this is doing is what that is doing. Okay, most vehicle suspensions, all vehicle suspensions, nothing is infinite stiffness. There's no such thing as a rigid body. Okay, we approximate that in academia, but when we have a spring, it has some stiffness. Okay, so will the sprung and unsprung masses follow the road profile identically? No. Okay, so we see the option no here. And then we see a few that says yes, and all of them have different justifications after them, but the answer is actually no. Okay, let's go through. Yes, but only for a step, which is a rectangular or square wave input. Okay, if you think about how a suspension operates, the step is actually the most aggressive case because that's, I think we had that discussion last week, this table brought up the good point, that's where the rate of change is the highest. Okay, so if anything, that's where they wouldn't follow the road profile. So this is definitely not true. The second one, yes, but only at the resonant frequency, or only at the resonant frequency of the unsprung mass, where R is equal to 10. Okay, so you can see here that your transmissibility function goes way above 1. Okay, so effectively what that means is that the question is asking, if your transmissibility here is 1, that means that y is equal to x is equal to z. So they're all the same. Every single displacement here is the same. Everything's moving rigidly. Okay, however, that only happens in a certain time. Sorry, a certain frequency and a certain damping. Okay, so that is definitely not true. At R is equal to 10, the system blows up and goes unstable. So yes, with no condition is also not true. We've just said that no is true, and then yes, but only when the damping is very low. So if you think about it, when the damping is low, the system will move more. There's less forces being transmitted between the plates, so the system will oscillate more. Okay, I'll show, yep.
You said
So that's what the question is saying. So will the sprung masses and unsprung masses follow the road profile identically? No, they won't. For a general car that doesn't have rigid suspension. If you ride on a bicycle that has no suspension, you can imagine that a lot of acceleration force is transmitted. Whatever the ground is doing, although there is some tire stiffness, if you pump up your tires very high in air pressure, whatever the road profile does is what you feel on the seat. That's what makes it uncomfortable when you ride over a bumpy surface. All right, the next question, this is where it's going to get interesting now because I'm going to do a demonstration with the rig as you answer the questions. So it says based on this square wave road input, so that's the yellow line here. Okay, you might not be able to see it on the TV screen, but you should be able to see it on your computer or your phone. So with the square road input of 0.5 hertz, frequency and an amplitude of 3 millimeters, what will happen to the sprung mass response, which is the blue trace here in this image. So you should be able to see that on your screen. When I activate the active suspension dampening in the system here. So I'm going to add additional dampening by doing that. So this is what the response looks like before you add the dampening. Okay, so you can see the road profile is the yellow, the red or orange response is the unsprung mass, that's the red plate here, and then the blue response is the blue plate here, which is the sprung mass. Okay, so you can see how they oscillate and they don't follow the road profile directly. Okay? So there's a few options. I'm going to let you guys look at those for a little bit, and I'm going to actually show you live what this does on the machine. Once everybody's given the questions to plot, right now you're looking at my laptop screen, no longer the podium screen, and that's open, has MATLAB and Simulink open here, and there's a model that is the full control model for this active suspension system. So there's a few inputs. Right now we have a general square wave input, which is coming from here. It's getting measured by this hold position, and then it goes through a whole bunch of these different filters and gain modules, adders, subtractors, and it's calculating the vehicle body velocity, the unsprung mass velocity. It's putting it through the governing equations for a 2 degree of freedom model, and then it's actively calculating how to minimize the sprung mass acceleration. So that's the acceleration of this plate here, so that it can change the damping coefficient on the fly. Okay, so what this is called is hardware in the loop. The hardware here is in the feedback control loop, and the computer is telling it exactly what to do. It's performing the calculations in real time. Okay, and then there's a whole bunch of outputs so that we can visualize the data. Okay, so I'm just going to click play here, and it's going to start oscillating the machine. So it's going down and up, down and up, down and up. And the amplitude is 3 millimeters, and the frequency is 0.5 hertz. So this is like hitting a curve with a height of 3 millimeters. Okay, so you can see how the shock wave is transmitted to the unsprung mass, and the unsprung mass is oscillating, and then that is transmitted to the sprung mass here. Okay, so right now this is with the active damping enabled. I'm going to disable it quickly, and you should be able to see how much more the unsprung mass is going to oscillate. So this is with very minimal damping now. So this, the active damping here isn't doing anything. Okay, I'm going to bring up the oscilloscope here, which is actually showing live what all of the sensors are recording. Okay, so you see this square wave input for the road profile, and then you see a whole bunch of overshoot and undershoot and oscillation of the unsprung mass and the sprung mass. Okay, this is with no active damping. Okay, this is what the question is asking you, so pay attention. I'm going to go back and re-enable the damping, and you'll see what happens to the response. sprung mass is much smoother. It overshoots a little bit and then it becomes almost steady state here in another half of a waveform. Okay, the unsprung mass is oscillating a lot, but we don't care about the unsprung mass really. So the forces that are getting added in the system here by the active damper are minimizing the acceleration on the plate here. So if I look at the acceleration, I'll go back to the map here, bring up the body acceleration. So let's go. Apologies, my laptop's a little bit old, so it takes some time to open. So you can see here the acceleration. So this is showing peaks and valleys for the live acceleration. Some of the side here got cut off on the screen. But I'll label the peaks here. So this is in meters per second squared. So 1.959 is, so let's say 1.9. There's a 2, there's a 1.7, there's a 1.9, there's a 2. So it's about 0.2 Gs of acceleration force is the peak acceleration force. So you could correlate that directly to that ISO standard for the ride comfort criteria. So that's how much acceleration force is getting transmitted to the user here. So if I had my cup of coffee on the blue plate here, you can imagine it would probably stay fairly still. Obviously it's not perfect, but it's a lot better than the other case. So remember the peaks here, how high they are. I'm going to disable the active damping. And now the peaks are about 50% higher, maybe 25% higher. So 2.5. So they went from 0.2 Gs to 0.25 Gs, give or take. Okay, they're actually, some of them are exceeding the scale of the y-axis there. Okay, so the question is for the actual quiz is how is the active part of the damping, what does it do to the system? Okay, so I'll keep this running in the background here. I'm going to switch back over to all the computer. Is asking what is going to happen to the sprung mass response, the peak of the sprung mass response. The amplitude will decrease, increase, more visible oscillations will occur. I definitely think that's not occurring here. Everyone should be able to deduce that. The peak amplitude will stay the same. So is the amount that this is moving up and down with the active system enabled, is it the same or is it different? Let's try and make this interactive. I don't want to just tell you guys all the answers, so raise your hand, please. If you disagree, or if you want me to do something with this that I might not have planned, raise your hand and say, can you see what happens when you change the frequency or when you change the amplitude? Okay? I'm going to do some cool stuff at the end. It's going to go unstable. It's going to make a lot of noise, so we'll get to see some cool stuff.
This is like not really but so in terms of like the stage, so like if you want to give me like, I'm trying to think of like at like you know as like essentially you know as he was in the way you made like behavior, is that like
yeah, I think what your question is, why is the steady state response not matching the full power directly? Is that what you're asking?
yeah.
So she brought up this point, and it was very good, and I kind of made over the last lecture, but it's because of gravity. If I start adding mass onto this, it's going to compress everything down. So as I add more mass, and we're going to do that, I'm going to take some masses and add them, you're going to see that it's going to match less and less. It's basically the system sagging. It's like me taking this car, and you can see how the suspension is obviously free now, and then when I sit it down on itself, it's lower. That's all you're seeing here. Okay? So the answer to this one is the peak amplitude will, who knows? decrease. So to compare the two waveforms, I just took a screenshot so that I don't have to keep switching back and forth. This is with the active system off here, so you can see the boom profile. And then this is the exact same view of the exact same plot, and you can see how much lower the peak displacement is for the boom profile with the active system on here. So I'll flip back and forth, and you can see how much less it is. It even oscillates less. Like this is almost perfectly damped. It overshoots a little bit, and then it reaches steady state, and it pretty much matches the unsprung mass response directly. Okay. Next question. What will happen when the road excitation amplitude is increased to 4.5 millimeters? This is a pretty intuitive question. Don't overthink it. Feel free, if you guys want to discuss amongst yourselves, just make sure that everyone answers their own session so that I know that you've responded to the question. Yep.
I have a question. So, because you're working at doing that,
Show you what is going to happen when we increase the road excitation amplitude. So this is the same waveform we're looking at live from the rig here. I'm going to go and increase the road amplitude here. Once the computer loads to This plate is moving less, this is moving less. There's a lot less overshoot in terms of magnitude. It's still oscillating, but I'll flip back and forth back to 0.45 so you can appreciate. So 4.5 millimeters. So now there's more displacement. This is, the amplitude here is now 0.45. Okay? So when we go back to the question, what will happen when the load excitation is increased. Displacements will increase, both the unsprung and sprung masses. They definitely won't remain the same. They definitely won't decrease. Okay? So increase is the answer there. So once again, I'll compare the two screenshots just so that we can go back and forth quickly. This is with the road excitation of 3 millimeters. So you can see the response here, and then the next slide here is 4.5. So I'll flip back and forth so you can see the response difference. So the percentage of overshoot is probably very similar. However, the magnitude of the overshoots is larger. Okay. Next question. If no other variables have changed, what will happen to the sprung mass response when an additional sprung mass is added to the system? Okay, so this is analogous to being in your vehicle, driving down the road, and adding more passengers to the car. So I'll give you guys about 30 seconds to think about it, then I'm going to demonstrate what it actually does. All right, for the sake of this demonstration, just because this roll of tape fits nicely around the sprung masses here and it's fairly secure without attaching anything rigidly, I just added about 500 grams to the plate here at the top, okay? So now I'm gonna run it again and we're gonna observe the response, and then we'll be able to discuss how it changed. So I will go back to the laptop here. You won't really be able to see a dramatic difference until we compare the screenshots, okay? So I did add some sprung mass, so back to his question, this line shifted down because I've added mass up here, all of a sudden the displacement is slightly lower because it's compressing the spring more, okay? So the blue line has shifted down, and the other thing that you should observe is this peak. Because there's more inertia on the mass plate, the rise time has gotten slightly longer or shorter. What do you think? Adding inertia to the system, what will it do to the rise time? Longer. Okay, so the distance between the input response, the input excitation, and then the amount of rise of the peak amplitude here should increase a little bit because the rise time got longer. Okay, so that's the answer to your question there. Go back and compare the screenshots. So this is what the response looks like when there's no mass added. So I just literally put a line here through the peak of the sprung mass displacement. Okay? And when we add the weight, I did this ahead of time. When we add the weight, the peak slightly shifts to the right. Okay, it's not a lot, but it's about 200 microns or so, 0.2 or 0.3 millimeters. You can't really see it visually, but you can measure it. And that's only an artifact of the laziness of me picking this small amount of mass to add. Okay, if I added a larger mass, obviously the effect would be exaggerated. Okay. So the next question, if no other variables have changed from what we just done right here, so the configuration of the system, what will happen if I add additional unsprung mass to the system? So I have this cell phone power bank here, and I'm literally just going to stick it on top of this plate here to add about, this is about 3/4 of a kilogram. Okay, so I'll show you what, I'll pause the machine, but think about it a little bit. We're adding inertia to the unsprung plate here now. Okay, so this is the effect of adding heavier tires and wheels to the system. Think about it, and then we're going to test it. Literally all I'm going to do is take this and slide it right here, just for sake of convenience. This is something that anyone can easily do. Just want to make sure it doesn't touch the edges to add additional friction. Okay, everything can still slide freely. Obviously it's not perfectly centered, but everything is aligned well enough that it doesn't matter a lot. For purposes of demonstration, this is sufficient. So now I'll click play, and you'll see that we've changed a little bit the way the system is going to respond. We've added inertia to this plate. I think visibly you can see it oscillating a little bit more. I'll change over the laptop screen here so you can see the response. And we'll look at the body acceleration as well. Okay, so the unsprung mass, this amplitude should have gotten slightly higher because there's more inertia in the system. The lag time or the rise time also got longer. Okay, so the oscillation somewhat is exaggerated now. So we'll go back and we'll compare screenshots. So this is with the additional strong mass only, so only the roll of tape before I added the battery pack there. So this is where the settling time occurs. Now I'm not going to compare just so that you guys get another term in your tool belt here. Now we're not comparing the peak, we're comparing when it reaches the steady state here. So that's defined as the settling time for the blue response. Okay? And this is when we add the unsprung mass. So the first thing that you notice is that both responses shifted down because that effect of the unsprung mass dragged the whole system down due to gravity. So the displacements all got lower. Okay? The other thing is shifted the settling time to the right in terms of time. So it added settling time because of the fact that you have more inertia on the unsprung mass. So we went from this. This is the settling time of the unsprung response here, the orange response, and it moved to the right by about 0.1 of a second. So we went from the effect of about 50 microns to about 100 microns here. Okay? Question 8 now. What will happen in response of the strong mass when I add additional springs? So I'm going to effectively increase the spring stiffness. So think about it, and then we are going to try it out. the additional masses that I added, just for sake of going back to the known configuration. And what I'm going to do is I'm going to take these 3 springs here from the RC car suspension, and I'm just going to insert it into the system here between the unsprung and sprung masses. So you can see how it lifted up this top plate. Okay, so now when I push on this, it's slightly stiffer by these 3 springs. So these are 3 additional springs in parallel with the 2 large ones that are here. Okay, so now we're going to test it out and see what happens. So keep thinking about what that's going to do to the system. In particular, we've just made it more rigid between these 2 plates because we've added additional spring stiffness. So conceivably, we should be able to see that this plate, whatever this plate does, this plate will more closely follow. Okay, this is a very dramatic change that we've done, and we're definitely going to see a difference in the response. Okay, so I'll click play. Give me 1 sec. I tripped the limit threshold here. I'll re-enable it. So automatically I tripped the limit threshold on the machine, most likely because the displacements are different, or the position of everything is slightly different. So in order to protect the machine from crashing into the top plate and the bottom plate, obviously there's encoders that know the position of everything, and it's feeding into the system here that can stop the actuator as a safety when something goes out of range. So I kind of went over that in the beginning just because, or I didn't talk about that just because it's outside the scope, but useful to know. So I'll click play now, and we'll look at the response on the laptop. So if you remember the unsprung mass response before, there was a really big overshoot and another peak. Okay, now you can see the signature here is totally different. There's a slight overshoot, and then it doesn't even settle, it goes to a larger overshoot. And these are combining modes now because we've changed the spring stiffness, and the unsprung mass is actually oscillating higher than the sprung mass now. Okay? The most important thing to notice here though is that the responses are more closely mimicking each other. If you remember the response from the previous configuration, the unsprung mass was oscillating outside of what the sprung mass was doing. Now both of these are doing the same thing to a higher fidelity. They're doing the same thing more closely. Okay? So I'll go back to OEM computer and look at the responses here. So the answer is the sprung mass will more closely follow the unsprung mass response. And to look at some screenshots here, you can see definitely this is the original configuration. Definitely there's 2 distinct peaks in the unsprung mass response here, and there's 1 overshoot on the sprung mass. And when we add the 3 additional springs, now these 2 curves or these 2 responses are more closely mimicking each other. So we went from this to this. And as you can see, the road profile is identical. We didn't change anything about the type of road you're driving over or the speed at which you're driving over the road. Okay, so that's all that's changed between these 2 is adding those 3 additional springs. Okay, so this is what happens when you take a vehicle and you make it sporty. You add those the additional spring rate, make it stiffer so that it has good handling characteristics, but you'll compromise on the ride. Okay, because this peak definitely got higher. Okay, this is the trade-off with suspension systems. All right, the next question, I'll let you guys read it for a little bit, then I'll read it out loud. Just to go back really quickly, if you can recall, if we the acceleration force from the user here, when the last time we looked at this plot, the peaks were about 1.9 to 2 meters per second squared. Okay? Now all we did compared to that configuration is add these 3 additional springs, and all of a sudden the user now is feeling 10% more acceleration force. So the ride quality should get worse as a result of adding those additional springs. The peaks went to 2.5, 2.6. Yep.
Is there an optimum point eventually, or is a stiffer system always going to perform better rates? Let's say you didn't care about their comfort. Would a perfectly rigid system be faster? Is there a point at which it's close to rigid but not that?
Excellent question. Just to repeat it, he's asking, well, is there an optimum system and do you really need the suspension? Because what this is showing you is that adding spring rate is not desirable for ride comfort. However, the response is here. This is following the road more directly, let's say, okay? And it improves the handling definitely because you're gonna remove body roll because the suspension is now stiffer. The answer to your question is yes. It is better to have a stiffer suspension, and you think, well, maybe you can just go to the extremity and make it infinitely stiff. And in theory, that would be good if the road was entirely smooth. As soon as you introduce bumps onto the road, your road holding capability is terrible when you have a very stiff suspension because you hit a bump and the car catches air or the car crashes into the ground because it can't follow the road because the suspension has no compliance. Okay, and it literally, you have all that inertia of the strong mass, and the wheel is just doing whatever the road wants to do, and it's not following the ground properly. Okay, there's too much spring force. The other thing, to answer your question, when we added these 3 additional springs, if we retuned all the dampening coefficients in the MATLAB Simulink model to compensate for this additional spring rate, we could probably gain back a lot of the ride quality we lost. So that 10% or 15% increase in acceleration force in the driver's feeling, we could gain it back somewhat if we added more damping. Okay, so it's a compromise. Yeah.
So basically when you're talking about like taking these systems to being rigid, right? You actually lose control because like normally if you have like a 2 independent systems of the spring, and when you move the spring, and like they remain in contact with each other because the springs work. If that is like infinitely stiff, if you put a force, it just becomes like projectile motion. It just pushes the car literally off the road because all that force is going straight into like basically kinetic energy, right?
Correct. So the more stiff you make the suspension, the more the strong mass trajectory is like projectile motion. You go over a bump, and it's as if there is no suspension at all. It leaves the bump at some exit velocity, and the wheels are just carrying with the vehicle. They're not actually following the ground. Okay, because it's transmitting all of the road profile directly to the strong mass, because it's infinitely or very much more stiff. All right, I'm going to make a final change to this model here, and we'll take a few. Maybe a minute or so to compile it. But now I've changed the excitation source. So what we had before was a simple rectangular wave input. Now what I'm going to input is white noise. Okay, you might say why. The reason being is if you're a savvy student, you might think, well, that's great. He simulated a very regular square input, which is a very repeatable response, but I've driven a car, I've been in a car, and that's not what the road profile looks like. Even the vehicle that we're going to be driving on the surfaces over there, that's a Habersign road profile that we're going to be doing, and it's a very regular profile. However, I've driven on a rough road, and it seems almost random. So what happens when you have a variable amplitude loading? So the bottom plate here, the road excitation, is just almost random. So what I'm doing is inputting a white noise now, which you'll see the effect of what it does in a little bit once this compiles. While I give this maybe another minute or so, does anybody have any questions on what we've got thus far? for anything you'd like to see, because I'd like to entertain any requests that you have after we do this. I can make the scrub mask go totally out of control and crash into the top. I can put a glass of water on it and make it fall over, although that probably isn't a good idea since there's electronics there, but you can appreciate how, if this is you, you want to minimize the acceleration force on that, because this is you sitting in the seat, this is you holding a cup of coffee, this is your inner ear and your equilibrium system in your body that will become dizzy or motion sick if you have excessive acceleration. And you're looking at a constant reference plane being, let's say, the horizon or the road in front of you. You're going to become feeling sick if you're constantly shaking up and down looking at something that's static. That's just physiologically what happens to humans.
Not exactly for the system, but would it be better? Would the position of the very top plate improve if we have multiple layers of the spring system? But I know right now we only have spring mass as a thing, but if we have another spring and another spring mass, would that improve the displacement of the
Great question. So if you think about how this is mounted in the vehicle, this is a more racing style suspension system, and the top, the way this is mounted to the car is very rigid. It's this aluminum plate here. Most luxury passenger cars have a nice rubber isolator mount here that will dampen a lot of the high frequency noise that's coming from the road that's getting directly transmitted through this stiff spring and the stiff dampening inside of here. So effectively that's like adding another spring. You have this nice cushion between the suspension and the body of the car. Also the tire, like the tire stiffness that we're having here is set. I never changed that. But your question here is maybe analogous to what about if I add 2 springs in series here, right? So they do that. It's called a progressive rate spring. And the purpose of that is that the more compliant spring will compress in the beginning, in basically the beginning of the bump, or if you're going over bumps at slow speed. However, if you make the suspension too soft because you've chosen one spring to be very low in its spring rate, you don't have any road holding capability when you go over big bumps. So you have a second spring that's a lot stiffer that only gets actuated in the extremities of the travel to add that additional anti-extremity force. So it'll hold the system in stability when you really go over large bumps. Okay? All right. So what we're going to do now is simulate that random amplitude profile on the lower plate here. So look at the response here. You can see now this is the acceleration. This is the plot we're looking at before. So now the road profile is just random step inputs. This is like driving over a cobblestone or a gravel road. This is what your suspension will do. This is what the body will do. Okay? So I'm going to disable the active damping. Right now we have it enabled. You're going to see how poor it is. anyone have any questions, or do they want me to try something unique with what we've done here? Or you guys want to move on to this here? Think about what just happened. We're going to go back and answer this last question in the quiz. So when you add, yep.
Can you apply science field to that?
Aaron, one.
Yeah, so that you can see that what the resonance peak frequency is getting in the model will it is same in this amount. Like R into 10 value. So 10 times the omega s value. So sine.
Great question. I'm going to show you all that cool stuff next week. So stay tuned for next week for that one.
About showing mass from mass to constant. Excitation is being covered. We show this is constant mass.
Okay, so his request is to input some excitation here and hopefully achieve the fact that the unsprung mass isn't going to move at all, or it mimics this.
It's almost like you're stable. It's exclusive law.
No.
And the lower position is actually very challenging. You don't do that.
Yep. So you might notice if you drive on a rough road, if you go at a certain speed, it will feel a lot worse when you speed up a little bit, and that might actually get better. Okay, and then if you slow down a little bit, it might get better. There might be some speed where you go over all the bumps and you don't feel very much at all. So I think that's what he's getting at. I would need to find that exact frequency for this machine, and I can prepare that for next week and do it next week. But I think the sine sweep will kind of achieve that, because you'll see as you change the frequency and you go from low to high or high to low, how both of these are going to start resonating and then become damped. Okay, so that's a great exercise. I don't think everyone's at the knowledge level yet to fully appreciate that. That's why I say it next week. Some of you that have more experience with your research work or other courses, you might really be eager to see that. Okay?
So the recent format for phase sideways, it's more predictable. It's able to truly right the way versus a random excitation.
The random excitation is difficult to tune for. Like what you were seeing there was somewhat random, but the actual amplitudes were random. The frequency was the same. So the spacing between each bump was about the same. It's just each bump was a different size. Okay, so what he was saying is sweep a varying amount of frequency. So that's effectively like accelerating from stop to some infinite speed over a bumpy road. So that's a great demo, and we'll do it next week. So the final question of the quiz: the ride quality will increase or decrease when we add the damping. So you saw when we activated the active part of the suspension, we minimized a lot of the acceleration on this top plate. Okay, so the ride quality should increase because the sprung mass acceleration will decrease. So we've minimized this acceleration on this plate. Okay?
You say the ride quality increases.
The ride quality will increase. Screenshots of what we were simulating there. This is the random amplitude profile. This is with active suspension off. So you can see how much oscillation there is on the unsprung mass, which is a blue response. And then when you add the active suspension or the active damping, you can see how much that was minimized. So almost by a factor of 2, we've minimized, especially here. So we have a huge amount of displacement on that peak, where this one is less than half of what we had in the previous division. Okay. So this is the last question of the quiz. Hopefully everyone appreciated that. We're going to move on to some MATLAB models that I posted on Learn, and then the remainder of this lecture is going to be focused on collecting data from that card. Okay, so before I move on, is there anything I can clarify? All right, so I posted 4 papers. Some of them are from journals, some of them are conference papers, and one of them is a master's of, I think it's a PhD thesis actually, that are simulating quarter car models. So this is what you have the option to create for this design activity. And I say the option because most of you have already committed to doing this. It's not mandatory. You can do any quantitative technique to develop a quarter car model. If you want to use Excel, if you want to use MathPad, if you want to use Wolfram Alpha, whatever suits you, you can use. But Simulink is very friendly. I made the model that you saw there, and that incorporated the hardware in the loop for this entire device. Okay, so that's a little bit more involved because there's an active component to the den. You're not taking that into account. You just plug in the static damping coefficient. Okay. So the 4 models are in the 4 papers that I posted on Learn. The first one's called the simulation of a quarter car model using MATLAB. And the cool thing is, in all of these models, they give you the parameters for sprung and unsprung masses, and they give you some stiffnesses and some damping coefficients. Okay, these are for real vehicles, so full-scale vehicles, not RC or smaller 10-scale models. So these values would be a lot higher than what you measure for those. Okay, but it gives you a point of reference, and it also gives you an idea of what the ratio of the unsprung to the sprung masses is, what the ratio of the stiffness to the damping coefficients are. Okay, so this is what the model is here. Sorry, the quality is a little bit poor in the PowerPoint, but you can see effectively you have some input waveform, and the waveform is going to be what we have there, that average sign. Okay, this is where your calibration case will be. And then there's all of these different components. There's integrators, subtractors, adders, gain functions, and all of these are available in the module library in Simulink, and there's descriptions of how they all work. Okay, so I'm not teaching you directly how to do this. The actual papers will show you what's required, but this is approximately how it will look. Okay, and the outputs, you can add some scopes here to have some visualization of what the response will look like over the average-side input. Okay, so everything in between the input and the output here is when you're effectively plugging into MATLAB. You can copy this directly. Okay, however, you need to calibrate it for your vehicle's data. There's a few options here. That's why I say you're going to select one. You might combine a few of them. You might take some elements from one, take some elements from the other, and combine them. But I'm leaving it up to you to create this on your own as a group. Okay. The second one is a passive suspension model using MATLAB for a quarter car and the input step signal type. So this is for a full vehicle once again. This is the mass of 1/4 of the vehicle, and then some stiffnesses and some damping coefficients. Okay. This is laid out slightly different, but it pretty much has the same elements: gains, integrators, subtractors, and adders. Okay. So you're coding graphically the equations that were presented in lecture number 8. Okay. Third model here is called line analysis of a quarter vehicle model. And once again, masses, stiffnesses, and damping coefficients. This one gives you for the suspension and the tire. So you can see how these are approximately different by a factor of 10. And the suspension, spring rate, and the tire rate here, how different they are. Okay, the tire is a lot stiffer than the suspension, maybe about by a factor of 3. And once again, this is slightly, the nomenclature is slightly different, but it's doing the exact same thing as almost the first model. Showing the proper here. By far my favorite model because it's the most clearly presented in this described is this one. It's called an active suspension quarter car bus model. Okay. Some of the parts here are active, however, you can just make them static. Okay, it describes this in the online literature. Once again, they give you the masses, the damping coefficients, and the stiffnesses, and this is taking an input signal here, input signal here. Okay, this is an active component. There's some sums, there's some gains, there's some integrators, there's some derivatives. It's literally just performing mathematical functions using these graphical laws. Okay, so if you're not familiar with MATLAB, that's okay. Like I said, you can use another method. You just have to predict the vehicle sprung mass response given this input that we're going to collect in the second part of this lecture. Okay? For a quarter car model, it doesn't even have to be a 2 degree of freedom model. You've hopefully collected enough data that you can make it 2 degrees of freedom and incorporate this unsprung mass. However, that's not mandatory. All right, so now I'm going to talk about what you're physically going to need to deliver for the end of the course. So in your design activity 3 group, submit the following to the design milestone Dropbox. I'll learn prior to next lecture, okay? Because you're going to need this because we're going to be testing models in the next lecture. You're going to get your response and comparing. Okay? You can still do some post-processing in the model after next lecture because the response paper might require you to do so. However, you will have to submit the model, and I'm going to take that as a point in time where you can make any additional modifications to the model. So from the experimental side, you need to submit the stiffness and damping coefficients. So as I mentioned, everyone should have the stiffness already. The damping, if you need to remeasure or take a high-speed video of the rebound phase of one of the dampers, they're available here for you to do that during the end of the lecture. So you need to do that from the quarter car with the experimental data that we collected in the previous lecture. The second thing is the video analysis of the unsprung mass. Displacement versus time, and the sprung mass displacement versus time for the quarter car. So now I'll describe what we're going to do over here. So I have this quarter car. I'm just going to bring it to the front so everyone can see. And there's an LED light that's hooked up to a battery that I take to the wheel. Okay? So as the wheel turns, the LED light is located approximately directly at the center as best as possible of the wheel. So that should stay at a level plane. So if I roll this down, here you can see it's fairly uniform, doesn't move. Okay? What we're going to do is we're going to turn the lights off and we're going to take a video of this driving down the track. Hopefully I can do this now here. Plug this in and I'll show you what we're going to do. Give us a second to connect here, but we're going to drive it down here with the lights off, and the video is going to effectively be set up here such that it's looking at the side profile of the vehicle and going over this funky profile. You're going to take that video. I'm going to give you a MATLAB script that might be useful for your future life, that you can extract the brightest pixel in the video and trace the vertical position of it. Actually trace the XY position as well. So what that is going to allow you to do is, based on the frame rate of the video, you can find the linear velocity of the vehicle and the vertical position of the wheel. So this is effectively tracing the road profile for you. Okay? And what that's going to allow you to do is get the excitation into the system. So that's what, in those MATLAB models, you're going to have is the excitation. And then we're going to take the LED and we're going to move it somewhere else in the vehicle, like right here. And this is going to represent how the sprung mass is going up and down as you roll the bumps. And we're going to drive it back and forth so we can take a few different data logs, and you're going to calculate the difference in that. And that's effectively your suspension actuation. Okay? So that's the difference between the unsprung mass and the sprung mass. So that's analogous to the displacements between here and here. Okay? We can also do the back of the vehicle if you'd like. However, time permitting, we'll see how far we get. Okay, so we're going to go on this road profile, and then we can simply change this up. Push this out of the way here. Move these here. Move these here. Now we have an out of phase haversack. So now when one side goes up, the other side goes down. Like that. Those are your two calibration cases. Okay? And I know a lot of you are looking at me right now like I wish I could do this 2 weeks ago so I could prepare. Part of this activity is to have a level playing field so that no one can prepare anything ahead of time. Okay? So this road profile is unique to this class, and the road profile you're going to get next week is also different from this one. It's not going to be dramatically different, but different enough that you probably won't have tested it already. Okay? So is there any questions before I move on to the last two things in the PowerPoint? So for the simulation part of the design activity 3, you need to create a MATLAB car model calibrated for that particular RC car. So you did most of the measurements last week. If you need to do any more, by all means, you're allowed to do that this week. And then the second thing is you need to predict the response for a unique road profile, and that road profile will be provided on Learn. So what we're going to do next week is you're going to actually get the new road profile. Okay, we're going to take another video of the same type of data. I'm going to give it back to you on Learn, and then your response paper is plugging in that road profile to your MATLAB or your Excel model or whatever you've done to give the response. Okay? And I'm going to be checking to make sure that your MATLAB hasn't changed between next week and the response paper. And as I mentioned, there's an asterisk here for MATLAB. You can use any similar method for quantitative predicting the sprung mass response. Excel, MATCAD, Wolfram Alpha, whatever you want. Okay? If there's anything to clarify regarding this, feel free to come talk to me throughout the next hour or so, because we'll be doing some measurements there as a group. All right, so everyone is going to get the same data. I'm going to upload video files that say unsprung mass front, sprung mass front, unsprung mass rear, sprung mass rear, for haversack in phase and haversack out of phase. Okay, they're all going to be video files. I'm going to record it maybe with a GoPro, maybe with my BlackBerry using small mode. You can also record videos yourself too, but we're going to turn the lights off, so that makes it slightly not dangerous, but make sure you don't bump into anything and trip over, okay? This is more of a demonstration. I'll get some people that want to help me complete the activity here, but I'm going to just basically be driving this over in the dark with the video camera set up, okay? You can observe or you can interact however you want to do it.
So when you're setting this up, to be honest, are you trying to do the
Flips? No. Let's see if this thing works now.
last week? Where are you at last week?
I went Toronto
For real? To party or what?
to meet my girlfriend.
Serious?
Yeah. Thanks, man.
Stuff like that. What happened?
He said he went to see his girlfriend in Toronto.
Last week.
Yo, congrats.
Look at this thing. So he gave us single card to all of the teams.
He gave us each card for one team.
All right, so this is the studio
So
part.
what is
Everyone
this
can-
thing?
you can work in your groups,
Video
you can watch
analysis and
the
first point
data,
mass.
you can help
Mass
people with the data, you can
That's for each different team.
converse
Yeah.
with each
Second
other,
point?
whatever you like.
I have videos, so like,
Set doing flips in the chart.
uh, yeah. So we have like that, and then it goes. It's like the video. We need to know like
How much time?
how much time it needs to get to the normal thing.
Okay.
So when we do MATLAB simulation, we have to change stiffness and damping coefficient until so we know that it takes that much time to get back to it. So we have.
Yeah, they do like basically progression. The problem is it only takes 1 point. That's my problem.
Which company?
So how many actual digits? We'll recognize this grayscale brightness. What do you recognize as we're doing manual
Nah, the boat's like very
What's your position? Yeah. What are you designing?
Like just trying to optimize the performance of the manufacturing line.
Try to what?
Optimize the performance of the line. You know the boxes that produce on the outside? Yeah. So you have the PLC programming and I'm like,
You know PLC?
no. My bullshit then. I'm good, don't worry. Give me the job.
You know PLC?
Not really.
How did they ask you? He doesn't know shit. What did they ask you?
Like, do you know PLC? Not really. Yeah,
Don't care.
for real. I don't want to get on
You're still owning a fucking game.
No, I got you, bro. Like,
Before I